Hello, my dear. Welcome to the IMS GATE Academy. I am Pragyabrat Tripathi. I hope your preparation are going in a very right direction. And to enhance your preparation, we are come in front of you with a series of score booster. Right. Now, in score booster, what is the motivation that we increase your score, we improve your score. Mind it, score booster, it is a type of activity in which we are boost your score, that means enhance your score, right? See, it is a just joking. If you have just scoring a cutoff mark, just to prepare for that, then you join the score booster. Why? Because in the score booster, we are coming in front of very intelligent question. And see, if you are not able to solve at that time, you don't bother about that. You are only aware that my preparation, ultimately my preparation are going on to that level. So if you are have a just see, there are two types of student. One is just a very serious student who appear in the gate, coming gate, and other is just trying. So if you are trying, also attend this score booster. Okay. So I am taking a score booster of fluid mechanics. Yes. See, you know all the things that the fluid mechanics is the common subject. And it is in the mechanical department and also in the civil department, right? In this session, today's session, I am coming in front of you with this simple topic. These are very simple topic. Some topics you already learn in the when you prepare the IITs exam. See, fluid property, fluid static, fluid kinematics, fluid dynamics, and boundary layer. Probably we'll take this two fluid properties and fluid static, other thing will next session, no problem. Okay. Now, in the fluid, if when you study a fluid property, some properties are very important. In that properties, frequently question previously asked, or there may be chance to ask in the next year also, yeah, in the coming year of the GATE examination. So fluid property, there is one property is very important known as viscosity. Now, if you read the viscosity, really, it will feel, it gives you feel in this subject. इस सब्जेक्ट में आपकी फीलिंग्स आएगी जब आप विस्कोसिटी को पढ़ोगे. विदाउट स्टडी द विस्कोसिटी, द वेरी इंपॉर्टेंट प्रॉपर्टी ऑफ द फ्लूइड इज द विस्कोसिटी, यू कैन नॉट फील द फ्लूइड मैकेनिक्स. So before the study of fluid mechanics, we just go through the one major property which sometime asked in the GATE, bulk modulus. This is your bulk modulus. You know what is the bulk modulus? What is the bulk modulus? See, bulk modulus is the measurement of a compressibility. The bulk modulus of elasticity, or simply the bulk modulus, is the measure of the amount by which the fluid offer a resistance to the compression. कहने का मतलब, see, if there is a fluid and the nature of the fluid, we'll discuss in the later. In the nature of the fluid, we take any fluid, at that point, there are a compressive stress will act. So in the fluid, there is a compressive force. That compressive force will resist by the fluid element, and that, what is that resistance? That measure by the bulk modulus. So in the case of bulk modulus, the fundamental parameter is what is the change in pressure. See, this is the relative parameter. That means what the change in pressure you apply to the volumetric strain. Why? Because you see, this pressure is the compressive, where it is Where it is found? From this force. You know that pressure is equal to force upon area, right? So from here we can find it. You have a force, you have an area, divide it, you take a pressure. That pressure is initial pressure minus final pressure. So this is your pressure. And what is the strain? This is the volumetric strain. This is the volumetric. See, my dear, the volumetric strain is the very important parameter when you are measuring the fluid property. Yeah, fluid. When you study the fluid, na, volumetric parameter is very important. Very, very important. We will discuss later on. No problem. So see, my dear, this is your original volume, right? This is your original volume. No problem at all. No problem at all. This is your original volume and this is your final volume. This is your final volume. This is your final volume. Okay? This is your final volume. We'll take like that. This is your final volume. So, what is the change in volume divided by the initial volume? This is nothing that, this is the initial volume. Right? This is your initial volume. So, you just divide that pressure, this pressure. See, there is a very important, there is a negative sign. Why this is the negative sign? Why? Because if we increase the pressure, the volumetric strain will reduce. So ultimately it will decrease. It will negative. But this is a property. That means bulk modulus is property. It is never negative. So to compensate that negativity from this equation, one is increasing nature, other is decreasing nature. So for the compensation, we put a negative sign. This is the very simple thing, no problem at all. Okay, now, so this is your bulk modulus. Okay, now in this topic, we will discuss some very beautiful example. What is that? Let's see. What is that, beta? Let's see. See, this is our first question. Just we see. Why we are taking some thought of the this theory part and after we will discuss the numerical. Why? Because you get a motivation that if we directly come on to the questions, this is not, you in your mind have a great feeling. So first we discuss about the theory part, then we will discuss the problem part. So there is a water subjected to a pressure increase. This is an increase in pressure. This is your increase in pressure, right? Determine the percentage increment in the density. Percentage increment in the density. Take, this is your volumetric strain is given 2.2 gigapascal. Okay. So I have a calci, no problem. I have a calci or not? Okay, no problem. So I have already calculation for that. Don't worry. We'll check a counter check. We'll take, no problem. So what is given here? My dear? See, this given. What? This is given. This is your, what is given? This is your EV is given, bulk modulus of elasticity. This is the elastic property. This is the bulk modulus of elasticity. This is your given how much? 2.2 gigapascal. Increase in pressure, dP, that means change in pressure is how much? 44 megapascal, right? You have to find increase in density. So increase in density, we have to find it. See, very important. Think like that. Increase in density. That means if the elastic properties is given, that means this is a material property, that material property is given, and the external agency, that means if we give the pressure change, what is its change in density? Why? Because beta, we also calculate from the bulk modulus property, the fluid property, bulk modulus, we also calculate the change in density, change in volume, change in pressure, anything. right? So see, if we see that m is equal to density mass density into volume, and if we Lm take log ln rho ln v, this is nothing, this is a volume. Okay, now if we integrate it, this is mass is constant, the fluid element, this element have a mass this element have a fixed mass m is fixed, no problem. Okay, so this mass is fixed, and this is what, rho by 1 by rho delta rho कर दो, 1 by v delta v कर दो. This is change in volume. And if we calculate what is the change in volume, volumetric strength, see the beauty, this is minus del rho by rho. So volumetric strength something related to also change in density, right? Obviously, why this is negative? If we increase the, that means if we decrease the volume, volume will decrease, then this will increase. So it is a negative sign. Yes or not? This R gives the negative effect. So there is a negative effect. So what is the increase in density? Right? What is the increase in density? So for that, we add some slide from here. It is not there, no? Okay. Add some slide. Nope. Okay. Listen. See, we'll do very slowly, no problem. Okay. Change in density. That means del rho by initial density. Let's suppose the mass, the element have initial density is rho 1. Now, what is that delta rho? Delta rho is final density minus initial density, and density mass by volume. So we can write like that, this m by v2 minus m by v1 divided by m by v1. Okay, no problem. If you calculate it, if you forget all the thing, this, if you cut all the thing, this v1 by v2, v1 by v2 minus 1. Now, why we are taking these questions? There is a one discussion, very important discussion. See, my dear, this is the very important discussion here. Why we are taking this question? Why we are taking this question? Why? Because see here, very important. When you calculate, when you solve the problem related to the bulk modulus, you have a challenge. You have a facing such type of situation, ratio of the initial volume to the final volume, or final volume to the initial volume. So how to manage? How to manage? See, for that, this is the trick. This is the punchline where you have to focus it. So to find initial volume to the final volume, this is our task. This is our task, to find final volume minus initial volume. How can you find? Just think. How can you find final volume minus initial volume? How can you find? See, you have, there is a given EV. It is given. Yes or not? It is given. Bulk modulus of elasticity is given. And from the bulk modulus of elasticity, we know that bulk modulus of elasticity is equal to minus dP by dV by V. Yes or not? Yes or not, beta? Okay? यानी सर आपका ऐप मोबाइल में नहीं चलता है, ऐसा क्यों? पता नहीं बेटा, I don't know. We'll discuss in the technical team. No problem. We'll decide. No problem. Okay. Missing lecture लिखा. Okay बेटा, no problem. Gyansam, no problem. We'll request the technical team. See that. Okay. No problem. So this is your, now this is given. This is given, beta. This is given. This dp is given. This dp is given. So you have dv, that means dv by v is equal to minus dp by ev. You have. So from here, this you have. This you have. So from here, volumetric strength. This is the volumetric strength. You can find it. Now, if now this is our add. Okay. Dekhiye, see. So we have, what is the we have? We just give taking a data. dv by v is equal to minus dp by ev. This is the trick. What is that? This is the motivation. Ki, sir, why we are calculating this? See, this is our motivation, that we have to find V1 by V2. This is your trick. Many students get confused here. How to find? So to finding this is the steps. This is the score booster. This is the boost to your score. So from where you can get punch, from where you can have a extra focus on that topic. This is your extra focus. How to find? Many students have a physical problem. So if you integrate this one, okay, no problem. So initial volume, final volume, dv, not dv, okay. Okay. V1, V2, dv, volumetric strength change into dv, v is equal to minus dp by ev. Okay, beta? ev. This is your pressure P1, this is your pressure P2. No problem at all. So this is a constant. This is your ln V1, one second, ln V1 by V2 is just, you just reverse it, delta P, V2 by V1 here, na? Here V2 by V1, we take negative, take care for that. So it is just reverse, delta P by EV. Now you have V1 by V2. See the beauty. See the beauty, my dear. V1 by V2 is equal to e पे power delta P by E of V. So this is your ratio. So what you learn here, that, sir, if you find the volume ratio, we just go through the formula. What is the bulk modulus of elasticity? EV minus dP by dV by V. And from that we can integrate and we find the ratio. And from that ratio you have this delta P, this E, this volume ratio. So from this volume ratio we can put here this equation. This equation, beta. Previous slide. From there, delta P by delta rho. Sorry, this is delta. This is delta rho, right? Delta rho by rho 1 is equal to, what is the V1, V2? What do you find? E pe power delta P. What do you already find? E V minus 1. See, this you already find, na? See, E delta P, okay? From here, you can put, what is delta P? See in the questions. What is the delta P, beta? Delta 44 megapascal, no problem at all. 44 megapascal, E pe power 44 megapascal divided by, see the very important, here is confusion in also in the unit. This is your gigapascal and this is your megapascal. When you are doing in a fast manner, put this value and get 0 marks. And get examination, the marks which is wrong is option number A. Mind it. Okay. So this is your if this is your this is your 2.2 into 10 to the power 3. This is your megapascal minus 1. What is your answer? This is 2.02%. Sure? 2.02%. See, there is a fluid. If you apply, what is the motivation here? There is a fluid. At this temperature, we apply the pressure. That means increase the pressure. That means you apply the pressure. Its density, and this is a fluid property. This is a material property. It is always given. It is always given. Don't bother about that. Okay. If you have an engineer in the steel industry, there is a data book from where, according to the material, you can get this value. No problem. This is given. Okay. In the machine design subject, sometimes this value is also remembered that in the interview question. What is the range? Range. They say it's still like that. Okay. So what is the density? How much the density is percentage change? See, the percent change in density is how much? Approximately 2%. See, my dear friend. See, my dear friend. If the density change within the 5%, if the density change within the 5%, we consider the element is incompressible. So it is nature. What type of the fluid here? What type of the material here? What type of the fluid here? This is incompressible. So water is incompressible. We'll discuss later on. Water is incompressible. So you always checked about that. If option is given A, B, C and D, see the beauty. Option is given 2% में 8, 5, 7. What's your answer? Without calculation, 2%. But if the answer is here is also given, some answer is also given 3%, na, then you are in problem. Then you calculate. But if there is a water, and we know that water acts as incompressible, so the density change for the incompressible fluid, the density change is within the 5%. Within the 5%, we calculate from the Mach number. No problem. We can calculate. If there is a detailed class, just now we have proved it. No problem. But it is not a detailed class, so we cannot go through that detail in manner. But you always remember, if there is water without any calculation, this is the score booster. Why these questions I have chosen? This is the reason. What is the reason? Number first, you have to calculate. Some other student have this option, read that water, get the option. That's it. Other thing, if there is a 2 option, how to calculate this answer, how to reach this answer, this is the process. Okay? This is clear? This is clear? Okay. What is that? Sing lecture. Okay, no problem. ठीक है बेटा. So this is one question, this is other question. फटाफट we'll complete this bulk modulus, then we'll go to the viscosity. What is that? Viscosity. I am giving you a challenge. You are not feel that concept previously. Okay? See, this is the second question. This is your second question. This is your second question. Okay? This is your second question. What is that? Just solve it. Just solve it, beta. I giving you time. Just solve it. Just solve it. Just solve it. Okay, beta? This is your second question. Just read. See, beta, if you are not able to solve a problem, simply you have to take 3 steps. 1, read the questions. Next, write the given data. Third, draw the relevant diagram. And what to find? If you do this type of activity, 4-step activity, ultimately you reach 50% of your solution of the questions. Don't think that this is a very lengthy question, and you may think like that it is not like supposed to be solved, but First, write the given data. Second, write, if there is a possibility to draw a diagram, you make a diagram. Third, what to find? Yeah, to find, right? So, like that, we calculate it, no problem. A sea water has a density. This is your density. This is your density. Sea water have a density, this one, at its surface. This density is at the surface of a sea water, right? Where the absolute pressure, see my dear, in engineering, which type of engineering? In the thermodynamics. If you deal with thermodynamics, or okay, or absolute pressure. Absolute pressure you always solve on the absolute pressure. Why? Because this is your positive pressure always. Absolute pressure, PV is equal to MRT. P is in absolute, T in Kelvin, right? So this is your absolute pressure, okay? Absolute pressure, this is the reference of a sea level, water sea level. At that point, the pressure is absolute zero. That means zero pressure, okay? Gauge pressure क्या हो जाएगा वहां पे? जीरो हो जाएगी एब्सोल्यूट, ओके बेटा? सॉरी, गेज प्रेशर है हमारे पास. जब गेज प्रेशर मेजर करेंगे तो वहां पे एब्सोल्यूट एटमॉस्फेरिक प्रेशर जीरो हो जाएगी, तो हम गेज प्रेशर पे चले जाएंगे. अब वही अगर गेज प्रेशर में हम एटमॉस्फेरिक प्रेशर ऐड कर दिए तो हमारा एब्सोल्यूट प्रेशर होगा. तो एब्सोल्यूट प्रेशर और गेज प्रेशर में ज्यादा कुछ अंतर नहीं है. एब्सोल्यूट प्रेशर में अगर एटमॉस्फेरिक कंपोनेंट को जीरो कर देंगे, एटमॉस्फेरिक प्रेशर को कंपोनेंट को जीरो कर देंगे, दैट मींस एटमॉस्फेरिक प्रेशर को आप डिफरेंट डेटम ले लेंगे तो गेज आ जाएगा. नो प्रॉब्लम, ओके. Absolute pressure is given. Okay, determine the density at a depth. That means if this is your sea water, okay, this is your sea water and this is your depth. Let's suppose this is your H. H is the depth. How much? 7 kilometer. 7 kilometer is the depth. Okay, this is your depth, 7 kilometer. And where the absolute pressure is, there is an absolute pressure P1 is given. P1 या P2 is given. And there is absolute pressure P1 is given. That means change in pressure also given. See the beauty? Change in pressure is always also given. Delta P, this is, let's suppose P2. The change in pressure is given. And at this height, what is the determine the density. That means what is the density at this point? What is the density at this point? What is the density at this point? How to calculate? I think you may calculate, is no problem. I think you may calculate. How it will calculate? See, what is given here? See, what is given? Sea water has a density. Sea water has a density at the surface. That means if this surface is 2, this is 1, I think this is raw 1, and we take this is your raw 2, no problem. Raw 1, raw 2, this is your P2 and this is your P1. Write all the data. I am writing that, no problem. To the speed calculation, I have a data. Raw 1 is given. Raw 1 is how much? 1030 kg. Why? Because we have a many problem, lots of problem, good problem. So we can write very speedily. And at that point, what is the pressure P1? 101 kilopascal. What is the raw 2? Raw 2 is also given. Yes. Raw 2 is not given. Raw 2 is found at the rate of 7 kilometer. We have to find it. Okay. Now, the pressure is given. P2, how much pressure is? 70.4 megapascal. You need to always remember. Right. So, delta P is given. This is the megapascal, this is kilopascal. Convert, it is in either kilopascal or either this convert into megapascal. Change in density. You take a change in pressure. So, what is the change in pressure? Delta P from here. Delta P is P2 minus P1. P2 minus P1. What is P2? P2 is 70 megapascal. And 70.4 megapascal. If you calculate this 0.1 megapascal, solve it. Delta P is how much? You just calculate it. Delta P is 70.3. 70.3. What is that? Megapascal. This change in density, see the beauty. This change in density, that means if you have at the sea surface and you go into the water up to 7 kilometer, the change in pressure is only reduce this. That means how much it will reduce? This will 70 point. That means this pressure will differ. Okay, right. Now, what is the calculation here? Now, how to calculate it? Add base. How to calculate it, beta? That means what up to that, what is the data? Delta P you have. How much delta P? Delta P you have 70.3 megapascal. Rho 1 you have, okay, rho 2 you have to find out. See, if there is a sea water going to the distance at H point, the mass, this sea water have a fixed mass is constant. When we are moving, the mass is not changing. Why? Because there is a reservoir, like a reservoir. The mass will not changing if you at this point, so there is a mass is not changing. So mass M of the sea water is not changing, is equal to density is equal to mass by volume. Yes or not? Density is equal to mass by volume. So mass is equal to rho 1, see the beauty, V1 is equal to rho 2 V2, and this is constant. Yes or not? So there is a one punch line. This have to thoughts. This line always come into mind when you solve this problem. This is the one click here. If you click it, your problem is 80% solved. Right. Now we have to find it. We have to find it with a rho 2. Okay. We have to find it rho 2. No problem. So from here, rho 2 is equal to what is that, beta? V2 by V1 into rho 1. Yes or not? Yes or not? See the beauty. See the beauty, my dear. Here also V2 by V1. So you have a concept how to find V2 by V1 from the bulk modulus. What is that? EV is equal to minus delta P delta V by delta V by V. So from here we again find V2 by V1. Put here value, find rho 2 because rho 1 you have. Yes or not? I'm giving 1 minute of time to find it. So from here, if you integrate it, delta V by V, delta P by EV, from here you can integrate it V1, V2, P1, P2. From here you can find V2 by V1. Now this time is negative. V2 by V1 you have E pay power. V2 by V1 or V1 by V2, no problem at all. V1 by V2 I think. 0, 2. Oh, there is a mistake. There is a mistake here. There is a mistake here. What is that? Just a reverse calculation. Rho 2 is equal to V1 by V2. So you have to find V1 by V2 here. No problem. V1 by V2. So you from here you can find V1 by V2. V1 by V2. Same previously slide. Same previous V1 by V2. Put this value. Same. Put this value. And this answer come to be okay. This answer is this answer rho 2. I have an answer. This density is 1.06 cross 10 to the power 3 kg per meter cube. Right? This is your rho 2. Okay, beta, this is your rho 2. This is your rho 2. Okay, so this is your rho 2. That means you have a density rho 1. What is the conclusion from these questions? This is the density 1030. Here is 1030. 1030. Here is the density C. That means 1060. This is your 30. Okay, no problem. हाँ, this is your kg, this is your kg. Okay, no problem. Just write, don't write this manner. If you write this point, na, pressure is this point, rho 2. So rho 2 is 1.06 cross 10 to the power 3. Again, while counter check, no problem. Kg per meter cube, 10 to the power 3 kg per meter cube. Okay. So this is your concept on bulk modulus. This type of problem you always supposed to be see in the examination, no problem, right? So this is the fundamental approach how to calculate change in volume. Now next, very important, is this one, viscosity. Viscosity, viscosity, viscosity. Okay, now if you are in, if you are in front of me now, I asked some very important and conceptual questions directly, but there is a time constraint. I just give you a feel. Okay, viscosity. If you think that many of you have, I think you're not supposed to that you get confused, but see in the fluid mechanics, अगर आप fluid mechanics को देखते हैं बेटा, अगर आप fluid mechanics को समझते हैं ना, तो fluid mechanics को बार बार रिवीजन करनी होगी. You revise repeatedly. If you not revise time to time, आप एक बार समझने के बाद भी दूसरे बार कंफ्यूज हो जाएंगे. इसलिए it is very important that you revise periodically. Okay, so beta, see, first is that I will prove that viscosity is the property. What is viscosity? Viscosity is the fluid that measure the resistance of the movement. किसका movement? Layer of the fluid to the adjacent one. The resistance occurs only when the tangential shear force is applied to the fluid. Very important. Very important. See, in this line, there is a very important line. See, this, for the time being, you just leave this one. Viscosity is the property, leave this one. This is the property, I know. Okay. But why this is the property? Under, see, now I ask some question. Question number first. Listen very carefully. Question number first. Why we called, see, this is the fluid. अगर आप इसको देखेंगे तो आपको किसी भी एंगल से लग रहा है ये फ्लूइड. ये फ्लूइड लग रहा है क्या बेटा? नहीं. आपको देख के लग रहा है क्या फ्लूइड ऐसा रह सकता है क्या? फ्लूइड ऐसा रह सकता है क्या? नहीं. But we modeled the fluid like that. We always modeled. We modeled the fluid always like that. So our question is that under which basis the fluid modeled as a layer? Under which basis fluid modeled as a layer? On which basis fluid को हम layer बोल सकते हैं? It will flow layer by layer. See, there is a first layer, there is a second layer, there is a third layer, there is a fourth layer, there is a 5 layer, there is a 6 layer, there is a 7. Yes or not? Yes or not, beta? Yes or not? So under which basis, यानी under what circumstances या under what thoughts, अगर हम आपसे कैसे कहें कि बेटा किस बेसिस पे आप फ्लूइड को लेयर में मान सकते हो, तो बेटा एक चीज हमेशा ध्यान रखना, हमेशा always keep in mind, if anything which which is able to deform, which is able to deform, that ability of the deformation, so that ability for what? Deformation. If there is any deform, you always consider that this is made of layer by layer. See, in the solid, it will deform. See, in the solid, if it will deform like that. Yes or not? It will deform like that. So it is also layer. Top fiber, bottom fiber. Top layer, bottom layer. So when there is anything which is able to deform, that due to that circumstances, that means deformation, if it is a circumstance that it will deform, then we consider that it will form different layer by layer. That means you have to consider fluid as a layer. That means fluid have to ability to deform. If there is no deformation, we cannot consider that fluid is in layer. See, if there is a fluid in a static, if this fluid, if we say that if fluid is in a static, there is no any deformation, then we cannot say this is in layer. So that in this case, we cannot consider the viscosity picture. If the fluid is static, we never consider that a viscosity. It have a viscosity, but there is no any effect. When the fluid is in a static, there is no effect of the viscosity. The effect of the viscosity only when the deformation, and deformation, there must be a layer. These are the interlink. There must be a layer. So when the fluid is under which basis the fluid considered to be a layer, only there is a deformation situation. If the fluid is deformed, we consider that layer. See, if there is a playing card, keep one into one and just drag it, it will deform. You think that there is a layer by layer. Then that is deformation. If there is no layer, there is no any deformation. Right? Okay. So this is the viscosity. Now, see, this is a little bit lengthy, but always keep in mind, beta, this is the physical mechanism. Always keep in mind. This is a little bit lengthy. You look like this is very lengthy topic. This is very lengthy statement, but you don't forget anything of a line. This is my request. ये आप कोई भी लाइन को छोड़े नहीं. ये लाइन बहुत इंपॉर्टेंट है. क्या कह रहा है बेटा? सी, उससे पहले मैं बताता हूं. उससे पहले कुछ पेज को ऐड करते हैं. देखिए बेटा, हमने क्या देखा कि जब दो सिचुएशन बना रहे हैं, वी आर ड्रॉइंग टू सिचुएशन. फर्स्ट इज this is your fluid. This is your fluid. Now, if this is your fluid and flowing uniform without any touching with the surface, so each layer, that means this is a layer, na beta. One layer, second layer, third layer. This is layer by layer. All the layers have a same velocity. All the layers have a same velocity. This is called uniform flow. What is called? Uniform flow. Now, the uniformity will disturb when it will approach on the solid surface. The uniformity of the fluid will disturb when it approach on the solid surface. That means if we draw at any cross section, if you draw, the uniformity is disturbed. That means all the layer have a different velocity. When all the layer have a different velocity, there must be a gradient. And if there is a gradient, so Newton say that देयर मस्ट बी ए shear stress. बट इसको लिंक कैसे करें? हाउ टू लिंक इट? सी वेरी इंपॉर्टेंट. सी बेटा, see we take this particle very nearer to the surface, then this particle just above it, then this particle just above it. Okay, this is particle number 1, this is particle number 1, this is particle number 3. Precisely, this is a gas molecules. Okay, what is happening when the fluid is approaching on the plate? Mind it, आप कभी भी you never found this type of things in the YouTube channel. Never found. Okay, so what is that? If this is your bottom layer, this is your just above, this is just above that. See, what happens when the fluid is approaches to the solid surface? First absorbed by the solid. First it absorbed by the solid. That means if this is your solid surface, if there is a fluid molecules, what happened to the molecules? What happened to the molecules? See, very important. What happened to the molecules? First, it will absorb by the surface. This molecule will absorb by the surface. When it absorb, it lose its momentum. Yes or not? It lose its momentum, and continuously the more and more molecules come into the picture, then again eject from the surface. Precisely, we are telling that one term, no slip boundary condition. No boundary condition. What is that? That means this fluid, if there is a no slip boundary condition, that means if you take this one in exaggerated manner, if this is your solid surface and if this is your fluid element, that fluid element have no tangential velocity. This fluid element have no tangential velocity. This velocity is 0. This velocity is 0. This velocity is 0. That means in the no slip condition, that means there is a no motion of the fluid. We cannot say that. There is no any tangential motion of the fluid. There is no any tangential motion of the fluid. Tangential direction में कोई motion नहीं होता. कोई motion नहीं होता tangential direction में. Right. How it will happen? ये कैसे होता है? How it will happen? See. What is the nature of the molecule? When will it strike the solid surface, it's just absorbed by the surface. After absorption, what happens? It will lose its momentum. It will lose its momentum. That means momentum disturbance. When the fluid, uniform fluid, will pass over the surface, its momentum will disturb. And that disturbance of the momentum is propagated from one layer to the other layer. From one layer to the other layer. That means this molecules, this is very important. These molecules, see, there is very interesting. Number one molecule, it is rest. It is happy. Yes. Why I am rest? Why? Because I am on the plate. So he know, number one particle is no. Yes, I am rest because I am on the plate. It is happy. But the second molecules want the justification. He says that my velocity is why not the free stream velocity. The molecule second is say that my velocity is why not the free velocity. Why my velocity is less than the free velocity? Though we are not touching the plate. अगर हम प्लेट पे नहीं है तो हमारा वेलोसिटी u infinite क्यों नहीं है? He wants the justification. From where we can justify that? If if it molecule, these two molecules want something, demand a question that, rise a question that my velocity is y naught u infinite velocity. Yes, your velocity, the fluid particle one velocity is a not infinite velocity. Yes, he understands that, yes, I am on the plate. No problem. But the point particle 2 is not on the plate, but the velocity is less than u infinity and greater than u 0. This u, the 2 velocity is less than u infinite velocity and greater than 0. Then he said that, why not my velocity is u infinite? See, very important. Same thing. 3 is said that, why not my velocity is u infinite? Why not my velocity is u infinite? Yes, I am not directly touch on the plate. हमारा velocity u infinite क्यों नहीं है जबकि मैं प्लेट से टच में नहीं हूं? Who's give this information? Who's give this message? From one layer to the other layer, how will give the message? कौन इसको बताएगा? ये चीज कौन बताएगा? Particle 2 का justify कौन करेगा? How to give the message from one layer to the second layer? That message will define the property known as viscosity. Known as viscosity. That means viscosity is a kind of a messenger. ये मैसेज किसके थ्रू जाएगा? मोमेंटम डिस्टर्बेंस के कारण. That means one fluid, this fluid have want to justify that it will adjust that. That means this fluid particle have a large velocity. This fluid particle have a zero velocity. So this two velocity, this particle will slow down this fluid particle. This particle will faster. ये उसको फास्ट करना चाहेगा 2 को, 2 को स्लो करना चाहेगा, तो 2 बेचारा डिस्टर्ब होगा, वो कंफ्यूज हो जाएगा कि ऐसा क्यों हो रहा है. तो उसको जवाब मिलेगा किससे जवाब मिलेगा? उसको मैसेज मिलेगा. किससे मिलेगा? विस्कोसिटी. दैट मींस विस्कोसिटी इज ए काइंड ऑफ मैसेंजर. दैट मींस दैट मैसेज विल प्रोपोगेट थ्रू द मोमेंटम डिस्टर्बेंस. थ्रू द मोमेंटम डिस्टर्बेंस. यस और नॉट? Yes or not, everyone? Okay. So there is a transfer of a momentum from the plate to the fluid, from the plate to the fluid. That means in this direction there is a momentum transfer. In that direction, there is a momentum transfer. And that momentum is transferred through the, and that momentum transfer gives rise the viscosity. Okay? So, that's why if there is a velocity gradient will exist, there must be viscosity. If after certain height, there is no any velocity gradient, see the beauty. See the beauty, my dear. Where the velocity gradient exists, there must be a messenger. That means there must be momentum diffusion. That means there is a diffusion that will transfer of a momentum from one layer to the another layer through the viscosity, through the properties known as viscosity, through the properties known as viscosity. But after certain distance, very minimum distance, after certain distance known as boundary layer thickness, this is a delta, boundary layer thickness. After, what is that? This delta is how much? Delta at the rate of 0.99 of u infinite. Above that, the fluid have, in the layer, there is no any momentum transfer. See the beauty? No any momentum transfer. Why? Because each layer have a same velocity. When there is a no any message pass, though there is a viscosity, but it is not feel I have a viscosity. ये feel ही नहीं करेगा. ये feel ही नहीं करेगा. See this. If there is a fluid, there is a viscosity. If there is a fluid, then there is a viscosity. But here the viscosity cannot come into picture. Why? Because उसको message देने वाला ही नहीं है. There is no any messenger kind. उसको message मिल ही नहीं रहा. Message किससे मिल रहा है? Through a momentum disturbance. Above that, there is no any momentum message propagation. So there is a viscosity, but not come into picture. There is a viscosity, but it is not come into picture. So the viscosity is the fluid property, but it is come into picture when there is a messenger. And messenger, when develop the messenger, how the develop of a messenger from one layer to another layer? There must be a momentum disturbance, momentum diffusion. How to diffuse the momentum? Due to relative velocity. Due to relative velocity. How to exist the relative velocity? How to exist the relative velocity? How to exist the relative velocity? Due to no slip condition. Due to no slip condition. If there is a fluid and will move parallelly, there is a no slip condition. So the origin, very important, the origin of a viscosity propagation, a messenger. See, there is a postman. There is a postman, and in the postman there is a letter. In the postman, in the hand of the postman there is a letter. Okay, and postman is deliver the letter from one place to the another place. The postman is a momentum diffusion. The postman is a momentum diffusion, and letter is the viscosity. Why? Because postman have a property to post the letter from one place to another place. If the postman have traveling without, that means a postman, that means a messenger, message dene wala, messenger. It is a kind of messenger. So momentum diffusion, that diffusion from one layer to another layer, through which the viscosity will propagate. The viscosity will induced. But here, though there is a fluid, but there is no viscosity, and that viscosity is known as dynamic viscosity. Dynamic viscosity. Why? Because it is due to momentum. Dynamic viscosity. Okay, this is due to dynamic viscosity. Now, next. Okay, now we can write like that. This is very punch line, beta. This is very punch line. Very important line. This is very important line, beta. This is very important line. See, what is that line? Viscosity, will write, no problem. Viscosity, will write. 1 second. This is very important line. Viscosity is a kind of viscosity is a kind of messenger one second beta गर्मी भी लग रही है रुक जा बेटा 1 मिनट viscosity kind of messenger viscosity is a kind of messenger from the momentum disturbance for the momentum disturbance from the momentum disturbance. So this is the disturbance of a momentum of the fluid. So this is the disturbance in the momentum of the fluid. Yes or not? Yes or not, beta? So this is the disturbance in the momentum. So this is very important line. Very, very important line. That means viscosity is the kind of a messenger for which momentum disturbance. Okay, and this momentum disturbance will induced, will come into picture when there is a no slip condition. When there is a no slip condition. So you always keep into mind. Okay, beta? Now next. Now, if you think about that, this is number first, number second, next. Oh, no problem. So previous one, add one. See, so if there is a plate, okay, right, this is your y direction, this is your fluid, okay, with a velocity u infinite. If we take any cross section, due the fluid is velocity is 0 due to no slip condition. After certain height from the fluid known as delta, the fluid have a velocity approximately u infinite, right, over which there is a velocity gradient will exist, above which there is no any velocity gradient. Okay, there is no any velocity gradient will exist. Okay, no problem at all. It is approximately u if in 0.99 of u infinite, but in the all calculating purpose we can take the delta, that means boundary layer thickness is at u infinite. Okay, no problem at all. This is your y direction. This u, that means there is a above that, what is that, and below that. Very important. There is a part A, this is B. That means this is the demarcation line above which there is no shear stress. Forget about the shear stress. First of all, forget about the shear stress. There is no any momentum diffusion. Why? Because all layers have a same velocity. All layers have a same velocity. Yes or not? Yes, sir. Yes, sir. Yes, sir. All have a same velocity. That means no momentum diffusion या transfer. Diffusion. In that there is a momentum diffusion. In that there is a diffusion, momentum diffusion. See, very important. If there is a momentum diffusion, there is a messenger. So viscosity come into picture. So there is a viscous flow. So there is a viscous flow. Okay, no momentum diffusion. तो ये मत सोच लेना कि viscosity नहीं होगा. Viscosity होगा. Viscosity is the fluid property, but there is no effect of viscosity. There is no effect of viscosity. That means if there is a no momentum diffusion, 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 there is a no effect of viscosity. no effect of viscosity. Right? Clear हो गया? Now, if there is a momentum diffusion, there must be a velocity gradient. There must be a velocity gradient. If there is no momentum diffusion, no velocity gradient. See the beauty. If there is a velocity gradient, that means in this region below this, this is the x, this is the direction of x beta. See, this is your x direction and this is your y direction. So below this, that means the line where the velocity is approximately 0.99 of u infinite, below this u किस direction? X direction is the function of y वाले. U का कौन सा component? Velocity का कौन? Which component of the velocity? X component of the velocity will vary along y direction. But above that, where there are no diffusion, above that, u is not a function of y. U is not a function of y. कहने का मतलब the gradient, that means du over dy is equal to 0. That means, what is that? U is constant. And what is the constant value? U infinite. What is the constant value? U infinite. This is clear? Basic thing. 99% in the interview, if you say that my favorite subject is fluid mechanics, immediately ask you in this context. I'm sure in this context always ask. Thank you, Saurabh sir. Thank you. Okay. Now, so this is the consequence. This is the consequence where the momentum transfer will take place, and what is the consequence where there is no any momentum transfer. So beta, in the fluid mechanics, when you study the viscosity, the concept of momentum diffusion, momentum transfer and momentum disturbance, these are all the synonyms, have to be very clear. What is the origin? What is the origin of momentum transfer? What is the origin of the momentum transfer? No slip condition. What is the viscosity? It is a kind of messenger of a momentum transfer. Momentum transfer will satisfy the fluid. Yes, I am not on the plate, but I have a velocity less than u infinite. Less than u infinite. Okay? Right, but less than u infinite. Now, there is one term here. What is that? What is that? There is one term. What is that? Kinematic viscosity. Kinematic viscosity. Kinematic viscosity. Very important. I am telling you, I am giving you questions that, sir, what is the kinematic viscosity? See, why the viscosity kinematic viscosity come into picture? Just I am telling you. But why the viscosity is the type of kinematic? Why? Because beta, if you derive the unit of this kinematic viscosity, mu by rho, there is no any mass unit. No any mass unit. Mass unit. That means this is your meter square per second. This is the kinematic parameter. There is no any mass unit. So this term is kinematic. But my question is that, sir, why we write kinematic viscosity? Why we cannot write kinematic viscosity is rho by nu? Why? Why we cannot write? Why we cannot write density by dynamic viscosity? Why we cannot write? You know, why we cannot write kinematic viscosity, dynamic viscosity by density? This type of question. That means we indirectly, I give you physical interpretation of the kinematic viscosity. Physical interpretation of the kinematic viscosity. Physical interpretation of the kinematic viscosity. See beta, if we think that, sir, this is the kinematic viscosity is mu by rho, right? What is mu? What is mu? It is a messenger. It is a kind of messenger to momentum diffusion. It is a momentum diffusion, right? Yeah, momentum disturbance. Yeah, momentum propagation from the plate to the fluid, from the plate to the fluid. So this is what beta we can write in a language manner, no problem beta. What we can write, one second, this is your, this, that means if this is your plate, if this is your plate beta, in this direction there is momentum diffusion. Momentum diffusion. There is momentum diffusion. In this direction there is a momentum diffusion, right? So this momentum diffusion, it is a kind of a messenger through which viscosity, that means viscosity is what? Is the fluid property, fluid is the fluid properties that try to diffuse the, diffuse the property that try to diffuse the momentum disturbance, that try to diffuse the momentum disturbance from one layer to the another layer, from one layer to the other layer. Okay, now what is this? What is this physical interpretation of the density? What is the physical interpretation of the density? What is the physical interpretation of the density? Density is, see, density is something related to the mass. Density is something related to the mass, and mass related to the momentum, inertia. Mass is related to the inertia. That means momentum, it will maintain the momentum. That means higher is the density, higher is the momentum. That means higher is the mass. If there is heavy mass, heavy inertia. Inertia effect is heavy, and heavy inertia, heavy momentum. That means this is what try to maintain the momentum. That means this is related to the mass, and mass is related to the, measure the inertia. What is that? Inertia effect. Mass is measure the inertia effect. What mass is measure? Mass is measure inertia effect, and this inertia, what is that? Maintain the momentum. See the beauty. See the beauty. That means it's try to maintain the momentum. Is try to maintain the momentum. That means, beta, that means if there is a plate, this is your punch line. This is your punch line. See very carefully. In this direction, there is a momentum disturbance, diffusion. In this direction, there is maintain the momentum. That means this is the relative indicator. That means this is a relative parameter. What is the kinematic viscosity? This is the relative parameter to which how much will maintain, how much the momentum will disturb and how much we will maintain. That means it is indicate that the relative tendency of the fluid to create the disturbance. That means we can write like that. We can write like that, beta. That means it is a relative tendency to, what is that? See, this is very important. It is that, it is the indicator. What is that, beta? It is the indicator. ये indicate कर रहा है. ये किसका indicate कर रहा है? Relative momentum diffusion to maintain the momentum. That means how the momentum will disturb and how much the momentum will maintain. That relative tendency, that relative parameter will measure by the kinematic viscosity. So kinematic viscosity is not like a gravity effect. It is not like a gravity effect. It is not like a gravity effect. This is very wrong. This is very wrong. It is not like a gravity effect. It only gives the indicator, it only gives the indicates to how much momentum will diffuse with respect to how much will maintain. How much will maintain? Why? Because beta, viscosity always lost the momentum. Viscosity always lost the momentum. That means higher is the viscosity, more and more loss of a momentum. But in that momentum, how much you maintain, that relative parameter will measure the kinematic viscosity. It is not measured by the dynamic viscosity. So the kinematic viscosity and dynamic viscosity both are different things. Dynamic viscosity only gives the indicator of the disturbance of the momentum. That means it mu, that means mu will always give the information that yes, this amount of momentum will disturb. Yes, this much amount will momentum will disturb. But the kinematic viscosity gives not only gives the what amount of the momentum will disturb, but it also gives the measurement how much we will maintain to that disturb of the momentum. That means this is a measuring parameter. Will measure maintain to the loss. That means this is a loss of a momentum. See, this is the motion of the fluid na. Are solo, this is the motion of the fluid na. This is the motion of the fluid na. That means you want to maintain that na. But the momentum will propagate from one layer to the another, from the plate to the. That means this will, what will create? This will disturb the momentum na. This will disturb the momentum na. Thank you, Sita. Thank you very much to support me always. When you hear the YouTube session, the Ishita will come into the picture and always support me. Thank you, Ita. So this will propagate the momentum and this will disturb the momentum and this will maintain the momentum. So this will maintain the momentum, this will maintain the momentum, this will maintain the momentum, and this will propagate the momentum. So how this will disturb the momentum? This is the disturbing momentum direction. This is the disturbing momentum direction, and this is the momentum maintained direction. So how much the momentum will disturb with respect to how much will maintain? That ratio gives the kinematic viscosity. It is clear? Everyone? It is clear? Okay. So when it is clear, so this one. See, how to define the shear stress? How to define the shear stress? हम shear stress को कैसे define कर सकते हैं? When the fluid is moving like that, how to define the shear stress? See, this is very important. I'm telling you, this is very important. Very important. See, see बेटा, अगर हम बात करें कि सर हमने तो we will discuss about the gradient, velocity gradient. We will discuss the velocity gradient. Why the velocity gradient will set, right? How it will measured. Okay, that means what is the physical consequence of the kinematic viscosity and what is the physical consequence of dynamic viscosity? Dynamic viscosity always measure the momentum disturbance. See, always measure the momentum disturbance. That means it is a messenger of the momentum disturbance. Kinematic viscosity what? It is a kind of messenger for which momentum disturbance. Right? Number second, what is the kinematic viscosity? Kinematic viscosity is not only the measure the momentum disturbance, but how can we maintain, how much maintain the momentum with respect to the momentum disturbance, that will measure the kinematic viscosity. That will measure the kinematic viscosity. Okay? Right. Now, see, if there is a plate, see beta, if this is your plate and this is your fix, okay, we apply the tangential force. We apply the tangential force. We apply the tangential force F. We apply the tangential force F. Okay? And that plate is moving with a velocity u. That plate is moving with a velocity u. Okay? So we take a, if we if you draw any cross section, see, this is your different fluid element. Okay? This is your different fluid element, beta. This is your different fluid element. Okay? This is your different fluid element. Okay? This is your different fluid element. Okay, beta? Now, when we apply the force, that means this force is the tangential force. Mind it. This force is the tangential force. Tangential force. This force is the tangential force. That means if we apply the tangential force on a fluid element, the fluid element must be deformed or distortion. Sometimes this distortion is the loose word, you know. Distortion is a loose word. Deformation. What is that? Deformation. See, what is the difference between distortion and deformation? What is the difference between deformation and distortion? You know? See, deformation, in that there must be a shape change. But distortion, in which there is a size change. That means deformation, there is a something deformed, the deformation will, the shape will change. That means due to deformation, for the deformation, we always require the tangential force. We always require the tangential force. For the deformation, we always require the tangential force, by directly or indirectly. But in the case of distortion, we always require the normal force. That means pressure causes the distortion and shear stress causes the deformation. That's it. Okay, so if you write a distortion, there is no any problem, but this is a loose sense. There is a deformation. So if the fluid will deform, when the fluid will deform, that means there must be a layer. If there is a layer and deformation, there must be a velocity gradient. Right? Okay, no problem at all. If you take any cross section, this is your y. Mind it, this is your y and this is your x direction, y direction. This is your y direction. Okay, beta? It is visible? Yes, okay. Y direction. We take any fluid element at this direction. This is your. Okay. We apply force F. And that we apply a force F, that means we drag, that means we drag the top fiber of the fluid that with the velocity u. Think like that. Okay, so the due to the no slip condition, the fluid which is stick to the plate have a same velocity as the top of the plate. What is the no slip condition? The no slip condition, it is the conditions are that the tangential velocity, in the case of tangential velocity is zero. Tangential velocity is zero. Yes, the fluid particle have a tangential velocity 0. This is not fluid tangential velocity. This is a top plate velocity. So the relative velocity of the fluid in the direction of tangent direction, in the direction of tangential is 0. Relative velocity, plate and fluid. So this velocity is only due to the plate, and this velocity is tangential velocity is 0. Why? Because the lower portion is fixed. This is 0. This velocity is 0. So this is 0 velocity, this is 0 velocity u infinite. There must be a gradient. We take a gradient in a linear manner. There is a many manners, like a parabolic, it is like that. So we take a simplicity, there is a linear manner. So if there is a fluid element, that fluid element have a deform, apply due to this force, that means force is equal to what? Shear stress is equal to what? Tau is equal to force upon area. That means this force is equal to what? Stress, shear stress, that means shear stress. This force is responsible to deformation, and deformation always gives the shear stress. Shear stress, okay? So velocity distribution within the thin fluid layer. This is thin. Why it is really thin? In generally, if there is a fluid is thin, the velocity profile is linear. The velocity profile is linear. What is the example? Example is ball bearing. In the ball bearing, there is a upper. Sir, pani pee lijiye. Okay. Thank you, Ankit. So, if there is a fluid element, if this is a fluid element, apply a tangential force, shear force. See, if we, very important, I am telling you, if you apply the shear stress, the cause is shear strain. The cause is shear strain, and this strain is angular strain. This strain is angular strain. This is angular strain. Okay? So this is a shear strain. This is a shear strain, and cause is shear strain. So, my dear, this is very important. I am telling you, we add. This is clear. This is strain, angular strain, del alpha. This distance between top layer and bottom layer is delta y. Okay, is delta y. Okay, no problem at all. If we say that, if you define like that, that means if you define the, see, for the solid, for the liquid, not solid, for the liquid, if you apply tangential force, if you apply a tangential force, that force is responsible to shear stress. Right? That force is responsible to shear stress, and this shear stress is created the angular strain. Angular strain. In the liquid, the nature is, in the liquid, yeah, in the fluid, you may say that, in the fluid, there is a deformation, and that deformation is continuous deformation. This is continuous deformation. You know, when there is a solid and there is a fluid, there must be demarcations. If you apply the tangential force on the solid element and if you apply the tangential force on the fluid, there must be a very, very, very different behavior. In the case of solid, if you apply the tangential force after the removal of that tangential force, the solid may regain fully or partially of its shape. It is necessary. But if we apply the tangential force on the fluid and when you remove the tangential force, fluid can never come back. Fluid can never come back. That means fluid have a zero memory substance. Fluid have a zero memory substance. That means the fluid is forget to come back. That means it have a zero memory substance. That means the fluid have a zero memory substance. That means deformation, not only deformation, it is continuous deformation. So there is a continuous deformation. If there is a continuous deformation, so you cannot define only strain. You define only, other than you define rate of strain. Rate of shear strain. Rate of shear strain. Okay. Now, and if you prove that one, so the velocity gradient rate of shear strain, you may write it theta dot. It is a theta dot, or you can say that this is alpha dot. Rate of shear strain. Rate of shear strain. Why? Because there is a alpha, na? There is alpha, na? So that rate of shear strain. So beta, we can prove easily the velocity gradient du over dy is equal to d alpha by dt. There is no problem at all. See, very important. In the fluid mechanics, rate of strain, that means shear strength, is not much more important as compared to the velocity gradient. But in the case of solid, velocity gradient is not much more important as compared to the strain. So, if you define the velocity gradient, this is our important parameter. It is not our important parameter. This parameter is only to equate this one. If you find analytically that the rate of angular strain is exactly equal to the slope of the velocity gradient. This is what? Slope of the velocity gradient. This is what? Slope of the velocity gradient. This is the slope. Slope of the, this is your dy, this is your du. Huh? Okay? No. This is your delta u. No, not at all, beta. This is your, if this is the velocity gradient, so this is your du, this is your dy. This is your dy, no problem. This is your dy, this is your dy, and this is your du. Okay, change in velocity layer by layer, right? This is your delta y, na? This is your delta y, na? Delta y over delta u. Okay, beta? This is your delta u, du. Okay, so this is your du. Now, so this is your angular response. That means we can say that the velocity, slope of velocity gradient, that means du over dy is equal to alpha dot. Rate of shear strain is equal to alpha dot. Rate of shear strain. Rate of shear strain. Rate of shear strain. Okay, beta? Yeah, rate of angular strain. इसलिए we can, this line is very important. I'm telling you, very, very important. Okay, beta? Next, see, very important. So du over dy is equal to d alpha over dt. This is equal to alpha dot. This is your rate of angular deformation, yeah, angular strain. Angular strain. Angular strain. Okay. And what is this? This is the angular deformation. This is also called angular. See, I am very happy to write something here. Why? Because when we write now, you may see the effect is very. If you, मतलब मैं कह के निकल जाता, I will speak and going for the next, so you cannot understand my feelings. So once we write, there is a very important to strike in your mind. Okay, no problem. This is the angular deformation. और बेटा rate of angular जो strain है, the rate of angular strain is measure the angular strength. Angular strength, very important. This is measure angular strength of the fluid element. Angular strength of the fluid element. Angular strength of the fluid element. So, which parameter will measure the angular strength? Angular strength. Very important, I am telling you. Angular strength, the measurement of angular strength is the angular strain. Due to angular strain, we can measure the angular strength. Now, this angular deformation, who is responsible for the angular deformation? Please write on comment. Ankit, Saurav, please write. Ghanshyam, who is responsible for the angular deformation? Who is responsible for the angular deformation, please? Who is responsible for the angular deformation? Who is responsible for the angular deformation, please? Ankit, Saurav, who is responsible for the angular deformation? Who is responsible for the angular deformation? Very late, yaar. Who is responsible for the angular deformation? Who is responsible for the angular deformation? See, my dear, the angular deformation is responsible for the shear stress. Who is responsible? Shear stress. Shear stress is the responsible for the angular deformation. That means who is responsible is this is responsible for the shear stress. This is responsible for the shear stress. That means the shear stress is responsible for the angular strength. That means, my dear, that means shear stress sometimes called momentum flux. Shear stress sometimes called momentum flux. How? How? That means called momentum flux. This is also called momentum flux. See, this is the score booster series. So I am not supposed to teach you very normal thing. Take a problem, solve it, take a problem. No, I will discuss here something something which is not frequently very much found into your YouTube channel. I am sure that. Okay, called momentum flux. Why the shear stress is called momentum flux? Shear stress. See, flux is what? Flux is what? The quantity which is per unit area. Flux is what? Which is quantity per unit area. Shear stress, there is a distribution. See beta. See, what is the shear stress? What is the shear stress? Force upon area, right? And that force is what? Momentum. Force is what? Momentum. Force is nothing, it is a momentum. The cause of a momentum is a force. Okay, so force is something related to the momentum. So momentum by area is called momentum flux. Is called momentum flux. It's called momentum flux. It is clear? So shear stress sometime called momentum flux. Okay, beta? Now, see. Okay, no problem. हाँ ठीक. Okay, बेटा. अब जो हमने पढ़ा क्या? हमने क्या पढ़ा? हमने जब ये पढ़ा तो अब अगर हम बात करें कि जो shear stress for the fluid is directly proportional to the rate of angular strain. Directly proportional to the rate of angular strain. Because this is the angular strain. This is your mechanics point of view. This is the mechanics. This is the mechanics. Rate, fluid mechanics. What is the difference between solid mechanics and fluid mechanics? You know? What is the very, very crystal clear difference between fluid mechanics and solid mechanics? The fluid mechanics, the stress is directly proportional to the rate of strain, and in the solid mechanics, the stress is directly proportional to the strain. That's it. Or you can say that if you apply the force, the solid may deform simply, but in the case of fluid, if you apply the force, tangential force, the fluid will continuously deform. The fluid is continuous deformance. So this is the fluid mechanics. And what is the solid mechanics? Tau is directly proportional to alpha. That's it. Tau is directly proportional to alpha. This is the solid mechanics. And this is your fluid mechanics. See the beauty? This is your solid mechanics. And this is your fluid mechanics. Okay? Right. And we know that if you remove that integration, we put some constant of integration. This is we move the directly proportionality, we introduce the constant. This is the constant into alpha dot. So this is called Newton's law of viscosity. 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 Okay. And we know that this angular rate of angular strain is du over dy. So what is tau? Tau is mu du over dy. This is your Newton's law of viscosity. This is for the Newton's law of viscosity, Newtonian fluid. Always it is applicable for the Newtonian fluid. Now, what is the importance of this equation? Anyone please? What is the importance of this equation? Anyone? That means tau is equal to this equation. Tau is equal to mu du over dy. What is the importance of this equation? Anyone please? What is the importance of this equation? What is the importance of this equation? The importance of this equation, we can easily measure, we can easily find the viscosity of any fluid. This is the very important importance of the Newton's law of viscosity. The importance of the Newton's law of viscosity is to find easily the property of the fluid known as viscosity. The property of the fluid known as viscosity. Okay, beta? Now, so we apply this equation. So we apply this equation and we find the viscosity of the fluid. How? See. This is your rotational viscometer. This is your rotational viscometer. It is visible? Yes, it is visible. See. See, beta, what is the rotational viscometer? You know that these things, we can easily find the viscosity. We'll introduce the viscous fluid inside this cylinder and we attached a string. Okay, one thing is known, there is a one hollow cylinder and there is a one solid cylinder. Okay, there is a one hollow cylinder and there is a one solid cylinder, right, through which, in which there is a fluid. This is your fluid. This is your fluid. This is your fluid. Okay, in this there is a fluid and the fluid have a thickness T. That means there is a gap, very thin gap, and in the thin gap the velocity distribution is linear. We already discussed. In thin gap there velocity distribution within the layer is linear. So there is a T. The solid, if we take, there is a string. This is a metal string. Metallic string. There is a metallic string, right? Okay. If we apply the angular motion of the rotating container is the outer container. Outer container is rotating, inner container, inner body is. See, why we are discussing now? There are very important chance to ask in the interview. What is the chance? That how to measure the viscosity through the viscometer. So you have to explain very clearly how to measure the viscosity on the viscometer. So viscometer, what is the arrangement? One is the hollow cylinder, other is the solid cylinder, and solid cylinder attached with the metallic string, and we apply the motion, we apply the torque. We apply the torque onto the outer cylinder. We apply the torque, that means we provide the angular momentum, angular motion omega, radian per second. This is radian per second, omega. We apply the omega on the outer cylinder, and the gap filled into the cylinder, or the gap of the gap which is filled by the fluid, which is measured, which can be measured of the viscosity of that fluid, and it is up to a height of h. Okay, so this is your view of a solid cylinder. That means this is your solid cylinder now. This is your solid cylinder, right? This is your solid cylinder. Okay, this solid, if we apply a torque to the outer surface, if we apply the torque to the outer surface, that means outer cylinder, due to the viscosity of the fluid which is present inside the fluid, the viscosity which is present inside the fluid will try to resist that motion, will try to resist that torque, and that resistance will transmit the torque to that solid, and the wire will twist it. Wire will try to twist. So what is the resistance torque? Yeah, what is the torque? Twisted torque to the metallic string. That means if you apply a torque to the outer fluid, outer container, the outer container is contact with a fluid of a viscosity fluid. That viscosity gives the resistance, and that resistance will transmit that torque to the metallic wire, and metallic wire want to twist. Metallic wire will try to twist. So what is the, this is the resistive applied torque and this is the resistive torque. On the metal there is a resistive torque. So the resistive torque will develop. See, if you apply the torque in the clockwise, in the anti-clockwise, the resistive torque will apply M momentum in the anti-clockwise with the radius Ri. There is a radius Ri. That means if you draw like that, there is an inner cylinder. There is an inner cylinder, beta, and that inner cylinder have a radius Ri, and it's apply a torque. It is not applied torque, mind it. It is a resistive torque. It is your, 1 second, beta. It is your resistive torque, okay? It is your resistive torque, T. You assume that it is a T, resistive torque. That means this is a vertical portion only. We can, there is a very important, we can consider, we neglect the resistive torque developed by the fluid which is present in the horizontal portion. हॉरिजेंटल पोर्शन का जो हमारा रेजिस्टिव टॉर्क है उसको नेग्लेक्ट कर दिया मैंने. हॉरिजेंटल पोर्शन का रेजिस्टिव टॉर्क को नेग्लेक्ट कर दिया. वी कैन नेग्लेक्ट, ओनली वी टेक है वर्टिकल पोर्शन. So this is your disc which is top view. This is your top view. Top view. This is your top view, right? Now, if you see this one, if you see in the large view, if you see this, so this is your fixed cylinder. If it is visible, it is okay. This is your fixed cylinder. This is your fixed cylinder. This is your fixed cylinder. And this is your moving cylinder, rotating cylinder. Okay. First you think that how the velocity will vary. So the velocity at the surface, see, very important, see beta, this is the fixed cylinder, surface of the fixed cylinder, and this is the surface of a moving cylinder. This is the surface of the moving cylinder in which there is a fluid. The thickness of the fluid, is, it is in R direction. It is in R direction. It is in R direction. Right? So at this age, the velocity is 0. Why? Because the surface is at a rest. So fluid particle at that point, the fluid particle at that surface is rest due to no slip condition, and the fluid particle which is at this point have a speed as the outer cylinder speed. So outer cylinder have a speed omega. So what is the tangential speed? This is the angular speed now. What is the tangential speed? This tangential speed is your, in this, what, this is your RO. This is your RO, right? From here, there is a RO, na? From the center, there is a RO, outer cylinder. This is your center, so RO. So RO into omega, very important. This is not RI. If you take RI, at RI, this is at RI. And this is your R at O. So at Ri, the velocity is 0. At Ro, the velocity is R omega. And there is a gap is very thin, so the distribution is linear. So the distribution is linear. The distribution is linear. This is like that. And the thickness is T. T is the thickness. That means a gap between that fluid layer. Gap of the fluid layer. Right. Now we calculate the metallic strip. That means what is the resistive torque on the metallic strip? How it will calculate with that? Just do it. How it will calculate? So what you to find? What we find? Torque. Torque. We find the torque first in the wire. In the wire. let's suppose this is T. T is the torque in the wire. Okay, beta? T is the torque in the wire. Right. If we find the torque, we first find the force. We first find the force. That means torque, force into perpendicular distance. This is nothing but arm length. Right? Force into perpendicular distance. And this force is the, this force is the tangential force. Tangential. This force is the tangential force. Okay, beta? And how to find the tangential force? How to find the tangential force? How to find the tangential force? From the shear stress. From the shear stress. How to calculate the shear stress? From the Newton's law of viscosity. That's it. This is your line diagram. This is your line diagram. You apply anywhere. You apply anywhere. Okay, beta? Now, so, right down. So, see the figure. See the figure. Previous one. See. If you find this force, so this force is Fs. That means this force is F. If apply a torque, this force Fs. This is your Fs. Yeah, F. You may say that F. This F force, who is developing? Who develop? ये force कौन develop कर रहा है? ये force कौन develop कर रहा है? ये force fluid develop कर रहा है. किस पे कर रहा है? On which one? Fixed cylinder. That means when you apply a force on a moving cylinder, the fluid which is at the surface of a moving cylinder is move as equal to the moving cylinder velocity. Once it will go to the fixed cylinder, the fluid at a rest. So there must be a velocity gradient. If there is a velocity gradient, there must be a momentum diffusion. If there is a momentum diffusion, there is a messenger known as viscosity. And viscosity is a kind of resistance. That resistance will develop this force. That resistance will develop this force. That resistance will develop this force. Sir, voice is coming very slow. No, beta. Excellent teaching, sir. Okay, sir. Okay, beta. Jayaprakash. Okay, JP sir. This force will be responsible. This force is how to induce this force? This force is due to resistance of the fluid. Right, okay. So this force into perpendicular distance. What is the perpendicular distance? Ri. So this force. So if we calculate, see, very important, T is equal to Fi into, not Fi beta, 1 second, not Fi, this is your F into Ri, this is Ri. Now how to calculate Fi? Same, tau is equal to F divided by area, right? And what is F? If you calculate in the form of torque, if you calculate this from this, what is the F? F is torque divided by Ri. So from here, if we take torque, tau, if you shear stress tau, torque by Ri, torque by inner radius divided by what is the area? Now there is a very important. What is the area? What is the area? See, the area is this area through which the fluid, this area. What is this area? Curved surface area. This is curve. That means, see, this is your fluid, na? This is your fluid, na beta. It is look like that. This is your fluid, na? This is the shape of the fluid, na? This is the shape of the fluid, na beta? This is your fluid. Yes or not? And this fluid have a thickness T. Only consider this vertical surface. What is the area? So this area is curved surface area. We write AC. And what is AC? AC. Curved. Well, 2 pi. Right? If there is a very minimum thickness, very minimum, you may take Ri or so this is your Ri. Inner radius basis, yeah, outer radius basis. Why? Because there is a very minimum radius. Okay. So AC is 2 pi Ri into this is the cross section area. Ri 2 pi R circumference into H. This H. So this is a cross section area H. Put this value back into this one. So there is 2 pi Ri into H. So this one is T by 2 pi Ri square into H. So this is your shear stress. This is your shear stress. Now, if you find this shear stress, T by 2 pi Ri, this is Ri. Now you have to calculate this du over dy. So there is there is a dy. 1 second. Dy is in this direction. Dr. There is nothing but dr. This is a dr. Okay. So this is your dr. So if you apply, add page. So now we have to find velocity gradient. Du by dr, not dy. Why? Because this is a r direction. So there is a change in velocity. What is that? What is that with a change in velocity? Du. Matlab that means the velocity change direction. This is du. Find outer velocity minus inner velocity. So what is du? R naught omega minus 0. There is 0. And what is dy? Ri ro minus ri. Ro minus ri. Like that. This is like that. Or ro minus ri is what? T. Ro minus ri is what? T. So from here we can put that this is your r naught into omega minus 0. This is your r naught minus ri. If you rearrange it, r naught omega divided by t. This is your velocity gradient within that layer. Okay, no problem. Put this one. So tau is equal to mu du over dr. So you have mu. So you have tau. Put that tau, shear stress. What is that tau? T by 2 pi I. T by 2 pi ri ka square into h is equal to mu. What is du by dr? R naught omega by t. No problem at all. From here we can find this t. From here we can find this t value, this mu value. So what is that? We arrange it. If you arrange it, this is your equation. We'll write it from that. Mu is equal to capital T into a small t divided by 2 pi omega r I square r naught square into h. Please check it. Please check it, beta. Please check it. Please check it. Okay. See, what is this? What is this? This is the thickness of the fluid. Thickness of fluid. This is your applied torque. Yeah, applied, not resistive torque. Yeah, applied torque. From where we can find the applied torque? Power. From the power. From power we can, from where we can find the torque? From the power. If you supply the power, easily you can get a power. Why? Because from here you start electricity. From the electricity you can get a power, and power is equal to T into omega. Yeah, you can find the power from the power. Force you can find that rotational tachometer. From the tachometer you can find velocity omega. You can find omega from here. See, and you can find the torque from the power. Torque you can find omega from the tachometer. You apply the tachometer, you find omega. Torque you can find the power. P is equal to T into omega. P is equal to T into omega. You find the torque. This is power is given. Find the torque. Omega. Measure inner dimension. Measure the radius of solid cylinder, which is rest. Measure the cylinder outer radius, outer cylinder radius. From where we hanging the viscometer. Find the vertical height. Put that one, you can easily find the viscosity. You can easily find the viscosity. Yes or not? You can easily find the viscosity. Okay, beta? This is okay? Now, this is simple, very simple, no problem. You can find easily from anywhere, no problem. Now, this is your next problem. What is that? This is your. Before that, we start this one. This one. This is your problem. See that. See this one. See this problem. See this problem. See, in this case, we find lower surface. This is your surface which is full of the fluid. How to compare it? See, very important. See, very important. In this, we can disregard the lower portion. We disregard the resistance due to the lower portion. In this case, we disregard the resistance to the lower portion. Only we consider the resistance to the vertical portion. We disregard the horizontal portion. So, if we talk about the net torque, so the torque due to the vertical portion plus the torque due to the horizontal portion. So, the torque due to the vertical portion is this one. Torque due to the vertical portion is this one, T. From here you can find T. And the torque due to horizontal portion is, now we can calculate. This is the footstep bearing. In the case of, I think, machine design, you may learn it, no problem. This is a footstep bearing, right? There is a cylinder which is moving. See, in the childhood, you can rotate your foot, this one to rotate one. That means your foot is placed on the solid surface. If there is a water, you can rotate very easily. So there is a this is your leg, this is surface, in this there is a fluid, and that is rotating with a torque T, applied torque T on this shaft. This shaft is rotating, with a angular velocity omega is equal to 2 radian per second. Omega is equal to 2 radian per second. The radius of this shaft, is 100 mm. The radius of this shaft is 100 mm, right? Now the shaft rests on the 2 mm. The shaft is rest on the 2 mm thick film. That means this is your thickness of the fluid, T. T is given. Thickness of the fluid is given. Film oil having a viscosity. The viscosity is also given. Viscosity, see, what is that? Newton second per meter square. We can write also Newton meter square. What is that? Pascal into second. This is also the unit of viscosity. Pascal second. You may remember it. Okay. Pascal per second. Okay. Shaft is rotating as a constant. Very important. Constant angular velocity. Omega. What is that? Constant angular velocity omega 2 radian per second. What is that? 2 radian per second. Determine the torque T. You have to find this torque T that must be applied to the shaft. The torque will apply to the shaft. To maintain the motion, this motion, that means you maintain 2 radian per second. To maintain 2 radian per second, what is the applied torque? So this is the applied torque. Applied torque. What is the applied torque? To maintain the motion. Assume the velocity profile is thin of the oil is linear. No problem. Thin. There is a very thin gap. So the velocity profile in that gap is very thin. Right? So it is look like that. See, this is your surface of shaft. This is your surface which is at rest, right? And in which there is a fluid. Yes or not? This is omega 0 and this have a omega. This have a omega. This will rotating. That means you think like that, beta. Very important. You put one palm down and other palm is up, and you poured oil or something, and then you rotate like that. This is fixed. This is fixed. Other palm is at the top. The top palm is rotating, and within that there is a fluid. Within that there is a fluid. So what if this is a rest? Due to the fluid, the fluid will develop the resistance because of viscosity, and that resistance to compensate that resistance for the rotation of 2 radian per second, what is the torque will applied? That means due to the resistance we apply the yes, Ankit, yes, you are right. So we apply the torque, right? If there is a high resistance, that means high viscous fluid, the rotation, that means you apply more and more torque. You apply more and more torque. So this is the same situation like that. Okay. Now how can you solve it? Please do it. No problem. How can you solve it? How can you solve it, beta? Please do. How can you solve it? Please try to solve it. give me a steps, no problem. Give me a steps, no problem. I will appreciate you. How to calculate? Ankit, how to calculate? How to calculate, Ankit? Please read carefully how to calculate. Why? Because it gives little bit extra concept. Okay. How it will calculate, Ankit? Please. How it will calculate? Okay. What is the approach? Ankit, Newton's law. With the help of Newton's law. Yes, it is right. What is the mathematical models? What is the mathematical model? What is the mathematical model? Just with the help of Newton's law, I know. We are all knows. With the help of, because there is a Newtonian fluid. But what is the mathematical model? What is the mathematics? See beta, this is your surface, lower surface. This is your upper surface. Right, very important. With the help of Newton's law, first apply the Newton's law. Tau is equal to mu d over dy. No problem. Just we will discuss viscometer. From that, you find the force. The force is the resistive force. Now, see, if this is your center line, right, this is R is equal to 0 and this is R is equal to capital R. Yes or not? R is varying from 0 to capital R, right? Very good, Ankit. Very good. Very good. We take a elemental force. Why we take elemental force? Many students get confused here. See, from this portion to this portion, the arm length is changing, right? The arm length is changing. See, if this at anyhow, see if the fluid is present in this ring only, the torque is different. If the fluid is present at this much area, the torque is different. If the fluid is present at this much area, the torque is different. That means dt. Yes, Ankit, very good. Then we calculate dt. Very good. So we take elemental strip over which the force is producing, and then we integrate with the applied dF into our torque is equal to at that force into arm length, then we integrate and we find the torque. Very good, very good. So we take this type of ring. This is a surface. On that, this is your center of the shaft. This is the center of the shaft, and we take one strip at any location from the center. We take one strip at any location from the center, right? So the location we'll take is R, right? And the thickness of that strip is dr. Thickness of the strip is dr, right? Now we apply the torque which have to be found out. This torque have to be found out. Okay. Now see, this torque will applied against which force? Why we can apply this torque? What is the requirement to apply this torque? Due to resistance. And why the resistance come into picture? Because of viscosity. If there is a more and more viscous fluid, more and more torque will be applied. That means this torque is something related to this resistive force dF. this resistive force dF. That means this is your resistive force. This is your resistive force, and this resistive force will try to decrease the torque which is applied. This resistive force will changing from R equal to 0 to R equal to capital R. See, if R equal to 0, there is no any torque. But if R is equal to capital R, the torque is maximum. If R is equal to capital R, the torque is maximum. That means from center to the periphery, the torque will change. And that torque is change is due to resistive force. So the resistive force will change. Right? That means if we find the torque, we multiply the radius, this radius. Which radius? This one, R. From that R, we multiply this dF and find the total torque. Okay? So, just do it. First, we apply the Newton's law. Tau is equal to mu du over dy, and that du over dy, right? So, from here, mu, what is du? See, outer periphery, what is the tangential velocity? Omega into, that means what is the tangential velocity? Not outer. Du was this, here is what? Omega into R. This is radius R. So this is your omega into R. Center, at the center it is 0. At the center there is 0 divided by thickness. What is the gap? Why? Because this is a vertical. This is your vertical gap. This vertical gap. This is gap here T. In this direction. This is your take Y. Okay, from the surface to the fluid. So from the fixed surface to the fluid. See, there is a very important information. The measurement of Y is from the plate to the fluid direction. Y is always fixed. This is measured always from the fixed surface into the fluid. This is the measuring parameter. Always measure from the fixed plate into the fluid. So the Y direction is what? Y direction is from the base to the fluid. And this is not in R direction. This is a Y direction. So from here we can take. With a dy, not dr. So dy, instead of dy we take t. So what is the shear stress? Mu d omega r into t. Now what is df? What is df beta? Stress, force upon area. What is df? Tau into dA. What is the dA? What is the dA? This is your dA. What is dA? What is dA? See, if you cut it, it is in a horizontal manner. So this is your dr. Thickness is dr. Length is 2 pi r. So what is the area? 2 pi r into dr. So this is your tau. What is the area? 2 pi r into dr. So this is your df. This is your df. Okay. Now put the value of tau. Mu omega r divided by t and rearrange it. 2 pi r into dr. Rearrange it, beta. Rearrange it. Rearrange it. So what is df? If we rearrange it, this is your 2 mu pi omega by t r square into dr. R square into dr. Yes or not? Yes or not? R square into, it is right. R square into dr. So this is your df. What is that? 2 mu, what is that, beta? 2 mu pi omega by t r square into dr. This is your df. This is the resistance force developed by the fluid element on the shaft. This is the resistance force. Okay, so it is always opposite to the torque. Okay, now if you apply, we find the torque, this force into perpendicular distance. What is the torque? Force into perpendicular. So this is your perpendicular distance, na? This is the perpendicular distance, and this is your df. So what is the torque? df into r. df into r. df into r. Put the value of df and r and integrate it, no problem. See, so what is its integration, beta? Put here value df. We'll check beta. We'll write t is equal to, we'll write final answer 2 pi mu omega by t 0 to capital R q into dr. Right, now solve it. 2 pi mu omega by t, this is R4, right, capital R4 by 4. Put the limit, no problem. Okay, so this 2 4 is cancelled out here, and this is your, that means applied torque T is, what is that? Pi mu omega R4 upon 2T. This is your applied torque. This is your applied torque. It is correct. Pi mu omega R4 by 2T. It is correct. See from here, if thickness will increase, that means you apply thick fluid. Thick. The torque will reduce. Yes or not? See, very important. If you apply the thickness, that means if you add this thickness of the fluid, the applied torque will increase. Yes or not? The applied torque will increase. Now, if we change the viscosity of the fluid and we place the fluid as a high viscous, again if the thickness will increase, applied torque will decrease. But if you increase the viscosity, applied torque will increase. More and more torque will have to be increased. If there is the same fluid and your gap will increase, the torque will reduce. Yes or not? If the gap will increase. See, if the thickness will increase, see, from the same fluid, see beta, very important. See, this is your hand, this is your hand, and there is a water, put oil, and if you apply, and if you want to rotate the upper pump, then if you press it, that means the thickness will reduce. If you press it and then rotate, its you have to produce more and more effort. Why? Because thickness will reduce. If the thickness will reduce, that means if you pressing it, if you press and press it, the thickness will reduce, the torque will increase. That means you want to more and more torque to rotate it. Likewise, if we decrease the thickness, that means if you separate the hand, if you partially open your disclose your hand, that means the interlocking between two hands will reduce between that same fluid, and you apply the torque, the application of torque will reduce. See, the application of torque will reduce. So T is always inversely proportional to the torque. T is always inversely proportional to the torque, right? So if we increase the gap between the footstep bearing, that means fixed surface and their bearing, if we increase the gap and then rotation is very easy for the same fluid. But the same place, if the gap will decrease, that means the thickness will reduce and reduce between the fluid between the surface of the rotating and fixed surface, the applied torque will increase. Same like the viscosity. If you increase the viscosity between that gap, the applied torque will increase. If you decrease the viscosity between the gap, the applied torque will reduce. Yes or not, beta? So we can write like that. It is little bit confusing here. Why? Because the same color, na? So if we write T is equal to pi mu omega r pe power 4 divided by 2 into T. So see, if we increase this thickness, the torque will reduce. Yes or not? Yes, obviously. If we increase this viscosity, the torque will increase. Okay, this is your observation. When you are studies now, you just not simply solve the problem. You just grab that concept. What is the motivation behind that concept? So we always try to derive the expression beta before entering the examination, and from the derivation you just from the numerical you just analyze yourself, so that you have accordingly you have boost your interviews also. Okay, now now we'll take this problem. No problem at all. Now we'll take this problem. This is your problem. Okay, just read it. This is your problem, beta. Just read it. Just read it. Just read it, beta. This is your problem. Just read it. Just read it. This is your problem. Just read it. You heard these things? Red wire. You know red wire? Hand handle music. You know this thing? Hand handle music. In old eras and at the old time, there is a disc. You placed it, over it we placed a one needle, and that needle is very minimum gap between the disc and the needle. The gap is 0.04 micrometer. This is your gap in between the needle and the disc. And when you try to contact that needle to the disc, automatically your player will start, right? So the surface area of the needle is given. The needle, that means red wire head for a handheld music player. The music player will start and has a surface area. This needle has a surface area 0.04. This is the surface area of this needle. The surface area it is given, right? Above the disc ke above, okay, no problem. Which rotating at a constant R rate. That means this disc is rotating at 1800 RPM. This disc is rotating at 1800 RPM, right? Okay. Determine the torque. Determine the torque that must be applied to the disc to overcome the friction, shear, frictional shear. कौन सा friction है? Shear. No भी लिखता चलता. Friction, shear, resistance of the air. See the beauty. In the needle and the seed and the player, music player, there must be a gap, and in that gap the fluid is there, and that fluid is normal air. Normal air. Okay, beta. So in that needle, that means, see, if this is your, see beta, if this is your disc, okay, if this is your disc, okay, this is your disc, and over which beta, this is your disc, and over which there is a needle. There is a needle, and in the needle there is a air. The needle is rotating, needle is fixed. This is your fix. Needle is fixed. And disc is rotating. So we have to find what is the torque required to rotate that disc, so that we design the motor, design the electrical circuit within that CD player. Why? Because for the disc rotation there must be a shaft, and the shaft we apply the torque. In the disc is mounted on the shaft, and the shaft, for the rotation we apply the torque, and this torque applied to be measured. Why? Because some energy, for the applied of this torque, the some energy will be wastage to the overcome of the resistance of the fluid which is present in between the disc and the needle. Disc and the needle. So for that we find the torque, right? And the disc, the surrounding air is at a standard atmospheric pressure and the temperature of the 20 degree. This property why it is given? Why? Because you have to know about the viscosity, dynamic viscosity of the air. I am giving you. Assume the velocity profile is linear. Yes, obvious. The velocity profile is linear. Why? Because beta, why the velocity profile is linear? Why? Because the gap is very minimum. The gap is very minimum. Now, right? Okay, beta, no problem at all. So we have to find it. First, I give you data, beta. Why? Because their dynamic viscosity is missing. So for the air, it is given mu value. This is for air. This is for air. It is given how much? 18.1 cross 10 to the power minus 6, very minimum, you know, Newton second per meter square. Okay, ठीक है ना? So what is the resistance, what is the torque which is applied to compensate the resistance of the disc, resistance of the viscosity. Okay, for that same situation we have to find the torque. So we have to find the torque, we have to find the force, we have to find the shear stress. We have to find the shear stress. First we have to find the velocity gradient, and there is a linear profile. So you know this edge is a fixed edge. That means a fixed path. This is moving at a fixed path, not a variable path. That means the resistance force is at this path. There is no any elemental resistance. Why? Because it is not moving like that. See, very important. If this lead is moving like that, out the center, yeah, toward the center, yeah, outward from the center, the resistance force will change. Why? Because along that the area of the air will change. The spread of the air, the dimension of the air spread will change. But it is rotating on a fixed surface. This is differ and this is differ. So this is intuitionally question will taken. This is other thing, beta. See, very important. This is your other thing. See, in this thing, the area will change. That means in this thing, if you draw the velocity diagram, see, if you draw the velocity diagram of this one, how we can draw the velocity diagram? See, this is your 0, this is your moving, and this will rotating. So at that point, the velocity is maximum and this point velocity is minimum. So there is a velocity distribution here, like that. So this is your center, this is moving like that. This is your velocity distribution. Which velocity distribution? Tangential velocity. This is R, capital R into omega, and this is 0. So why it is changing? Why? Because beta, the fluid has continuously spread. Here the fluid is continuously spread, but the radius will not change. Radius is fixed. That means a needle is rotating at a fixed radius. Okay, so we'll take this one. So for this one we take this for this one we take, this is your surface. This is your surface. The curved surface, we are drawing a flat cylinder, a flat surface. This is a curved surface, na? This is your curved surface, na? We are drawing a flat surface, and over which there is tangential velocity, na? R into what? 8 mm into omega. This is tangential, and here the tangential velocity is 0. So from at the needle, no, not from, if you measure this one, so at the surface of the CD of the player, the velocity is, you have find it, how much velocity you can find it. What is the omega? 2 pi n upon 60. This is the lower play velocity at the player. What is that? 2 pi n. N is 1800 divided by 60. This is your 60 pi radian per second. This is your omega. Right, first of all, we take this one. Okay, no problem. This is your omega, right? Now, what is that U? Velocity of the CD player, R into omega. What is the R? R, you know, this is your R, 8 mm. 8 cross 10 to the power minus 3, yani 0.008 into u into omega 60 pi. If you calculate it, it is your 0.48 pi meter per second. This is your tangential velocity at the CD of the music player. This is your tangential velocity at the CD of the music player. So this is your tangential velocity. Now this is your tip. This is tip, contacting tip over the CD of the cylinder, CD of the disc. This is the velocity is 0. Why? Because it is a fix. At that point it is a fix. Only disc is rotating. So this is 0. So there is a 0 and there is a maximum over which there is a velocity profile and the gap is very thin. So there is a linear velocity profile. It is clear? All of you? It is clear? All of you? Right. Okay. Now, if you think about the torque or resistance torque, what is the torque? So if you take a circle over this periphery, if you take a circle, right, and if the disc is rotating anti-clockwise, the resistance torque will develop. That means resistance force. Disc will rotate. That means applied force is in anti-clockwise. Then the resistance force due to the air viscosity is in clockwise. So it is in clockwise. See, it is in clockwise. See, it is in clockwise. At a fixed radius, it is in clockwise. It is in clockwise. This is your force. This force exerted, this is the resistance force. This force is exerted by the air on the disc of the CD player. Okay. So what is this force? We calculate, and this is the radius. How much? How much beta? 0.008 meter. Okay. And this is your applied torque T. This is your applied torque T. Okay. Now we calculate the velocity variation, and the thickness is also given. Thickness is given or not? 1 second. Thickness is also given, beta. Thickness is 0.04 micrometer. So 0.04 cross 10 to the power minus 6 meter is the thickness. Am I right? This is your thickness. Right, beta? So this is your thickness. Now we find the velocity variation. That means du over, this is what direction? This is thickness direction. This is y direction. Du over dy. So du over dy is equal to u at the surface of the disc minus 0 divided by t. This is t beta. Du over dy, this is equal to u minus 0. U is the periphery. U is the periphery at the CD disc. Y at the point y is 0. Yeah, t. Their gap is t. So this is what? U by t. So u by t is du over dy. Du over dy, u by t. So what is u? What is u, beta? 0.48 pi divided by t. T is what? 0.004 cross 10 to the power minus 6. Okay, yes or not? You can calculate it. So what is du over dy? Du over dy is 12 cross 10 to the power 6. I think so. 12 cross 10 to the power 6 pi. What is the unit? Du over dy. What is the unit? It is the same unit of the gradient. That means u meter per second. This is your meter. So it is per second. That means second minus 1. So this is your d over dy. You have to find d over dy. You have to find d over dy. Now the next target is shear stress, tau. What is the tau? Add. What is the tau? Tau is mu d over dy. You have mu. You have mu. You have d over dy. Put that value. What is the mu? Just you tell me. What is the mu? Previous place. What is the mu, yaar? Just tell me. 18.1 cross 10 over minus 6. Just tell it. 18.1 cross 10 to the power minus 6. This is your mu. What is d over dy? What is d over dy? 12 cross 10 over 6 pi. 12 cos 10 to the power 6 pi. Just solve it. So this tau is how much? Just calculate it. 217. Just write it. 217.2 pi. What is that? Newton per meter square. This is a shear stress. Now, you find the shear stress. Now you find the force. What is the force? What is the force? T into tau into shear stress into area. What is the area? What is the area? This area is the contact area. And what is the contact area? What is the contact area? This contact area is given 0.04 mm square. So from 0.04 mm square, just change the dimension. 0.04 cross 10 to the power minus 6 meter square. This is your area, that contact area of this needle. This needle, that means the needle have this contact area. This contact area AC. Okay. So tau is what? 217.2 pi cross, the cross section area is 0.04. 0.04 I think so, no? 0.04, yes. Into 10 to the power minus 6. 3 nice. Minus 6. Right? If you calculate it and pi is there also, no problem. It is, if you calculate it, this is your 8.6. How much it is? 8.688 cross 10 to the power minus 6 pi Newton. This is your resistance force. This is your resistance force. Now, if you find that this is your resistance force F, and now if you find the torque, so this resistance force into arm length, this resistance force into arm length. So what is the torque? T, this force into R. What is this resistance force? 8.688 cross 10 to the power minus 6 into pi into R. What is the R? R is there or not? Yes, R is given. 8 mm. 8 mm. So it is 0.08. 0.08. Right? 0.08008. So it is how much? Calculate it. It is approximately 0.12. It is approximately. See, it is approximately 0.218 pi. What is that? Newton meter square. That means this torque is extra you will provide to that angular motion. That means, see, if there is air, air is have a resistance, so it will resist that torque which is applied to you. And how much it will resist? This is your resistance. So at this extra torque, you will apply to overcome that resistance. Overcome that resistance. So these are the today's session. Now some more question is left. We'll discuss accordingly in the tomorrow sessions. We'll continue from this at this stage, no problem, and start with that numericals and also theory, right? After that, in the fluid mechanics, open channel flow will take by the another faculty, which have a very good faculty of the civil engineering. So you may also join. Why? Because if you attend this fluid mechanics along with the open channel flow, then you have a score for the particular civil engineer. Civil engineering have a more weightage for the open channel flow. So a particular for the open channel civil engineering student, you must attend the open channel flow. If you not able to attend the open channel flow, this session is useless to you, useless to you. Okay, so you must be attend. Mechanical engineer, just attend today's. You have to attend today's classes and tomorrow classes. That's it. That in that situation, we have to find very good questions and concepts so that you can able to discuss anything for the anyone. Okay, for the anything for the anyone. Okay, beta. Thank you. Bye bye. Bye.